Okay, ladies and gentlemen, this is going to be our heating curve notes that we couldn't take in class, and since I'm not here today, you'll have to take notes along with the video. Now, you should have gotten the heating curve notes. If not, you can find them on Echo and print them out. So when we talk about heating curves, the first thing that we want to talk about is the first law of thermodynamics, because essentially what we did in the lab was we changed the thermodynamic state of something, the ice and water. Now, the first law of thermodynamics states that energy cannot be created or destroyed. Cannot be created or destroyed. So really what that means is energy is transferred, and like the hot plate transferred energy to the water and ice so that the ice heated up. That energy came from somewhere with the intent of increasing the motion of molecules. So we had thermal energy from one source that added thermal energy to another. Now this involved heat. The two types of heat that are relevant in this case are kinetic energy, and potential energy. Now you may remember from physics, potential energy and kinetic energy are two types of energy of motion. Now, kinetic energy is the energy of motion. Okay? Energy is stored energy. So we often call it the energy of position, but it really deals with the fact that it's energy that's already in the substance while it's at rest. So those two types, oh, sorry, I forgot to fill out motion. Okay. Now, potential energy is stored energy, and when we move the potential energy into kinetic energy, we call that heat. So heat is what we call the energy that is or the process of transferring energy. Heat is not a substance. You can't add heat to things. You can only add kinetic energy or potential energy. However, for convenience sake, we call that heat. Now this brings us to heating curves and phase changes. Now a heating curve shows the change in kinetic energy of a substance. So the change in kinetic energy. Sorry, I didn't leave enough room there. Okay, so it's the change in kinetic energy. This involves something heating up or cooling down. So either the particles are increasing motion or the particles are decreasing motion. Now, that change in kinetic energy is measured by temperature. Okay, so we use a thermometer to measure the kinetic energy of something. So if something's at 60 degrees, it has so much kinetic energy. But if it's at 120 degrees Celsius, it has more kinetic energy than 60 degrees. Which brings us to the idea of phase changes when we heat or melt something, because that has to do with the motion of the molecule. What happens is the phases of a substance and I'm going to give you a second to sub. The phases of a substance change as it is heated or cooled. So, like in the case of boiling water, we heat it up, and the liquid particles move from one type of motion to another type of motion, they're very close together and they're moving at, let's say, an average speed. But as we heat it up, that speed increases until the molecules get so much energy they can break apart from one another. So this idea of phase changes and changes in kinetic energy can be graphed with a heating curve. So a heating curve measures the changes over time of the temperature. So the temperature over time as it changes. Now, one thing we may see is it increases. Like, I want you to imagine we have a block of ice, okay, that's very, very cold, and let's say -10 degrees Celsius. Then it heats up, but they're at that 0 degree mark, which is the melting point of water, it levels out. That's because now the particle here, the particles are very close together for an average substance. Water is a little different, but we'll talk about an average substance. Whereas in this phase change, we have some that are close together, and we have some that aren't. Okay? Now, the reason the temperature levels out is because any energy we're adding is being balanced by energy that's leaving. Okay? Now, once it's all melted, we get another section of the curve. And then it starts boiling. So we'll call that 100 degrees. This graph isn't to scale, so bear with me. Okay? And once again, we have particles that are a little close together. And then we have particles that are very not close together. Okay, so we have a liquid phase and a gas phase simultaneously. Down here we've got a solid phase and a liquid phase simultaneously. Now, it's flat for the same reason. Some of the substance is a liquid, and any energy we put in is actually being transferred to that gaseous part, the steam, the boiling. This is why the boiling point of water, the temperature stays the same for a while. Then, once all the particles are gas, they start to heat up again. So we have the gas, we have the liquid, we have the solid. But then here we have melting, here we have boiling. Okay, so this is the actual phase change. These are just phases. So this is an example of a heating curve. And we call it a heating curve because the temperature is actually increasing over the course of the graph. Now, a cooling curve is a little different. Let me grab a different colored pen real quick. A cooling curve would be the opposite. I'm going to draw it over here. I'm going to try to draw it over here, where we still have time and 10. Oh, sorry, I realize now you can't see. A cooling curve just goes the other way. So this is a cooling curve. Okay? So heating curve, cooling curve. But they essentially show the same thing. They show a single phase, they show two phases, single phase, two phases, single phase. Okay? So changes in temperature in this case represent changes in kinetic energy. I'll run my knuckle with that. Changes in kinetic energy. So as we go up the heating curve, our kinetic energy is increasing. as we go down the cooling curve, our kinetic energy is doing the opposite. It's decreasing. Okay? So single phases are sloped lines, where we see only solid, and it's getting energy that's causing the molecules to vibrate more and more and more until now in the melting phase they start to break apart. But once again, all the energy we're putting in to the solid is actually going out to the liquid. So the average temperature does not change. The same here, liquid, it's increasing until we get to the boiling point, at which case all the energy going into the liquid goes into the gas. And then once we're all a gas, the energy just keeps going. Okay? Because in order to get to a plasma, something special has happened that's beyond the scope of our heating curve. Now, single phases are sloped, but a flat line is a phase change. We talked about this already, but it bears repeating. Now, keep all this information in mind because you're going to construct heating curves and cooling curves. Now, let's see if I can actually show you the whole paper. I cannot show you the whole paper, but here's the bottom. You can go ahead and pause it if you need to. And here's the top. Once again, you can pause it if you need to. So if you have any questions, feel free to write them on your note page so that you can ask them in class later. Otherwise, I will see you guys later.